This lesson is for section 1.5 on continuous functions. We have two objectives for today. We're going to determine if a function is continuous at some value of x. We're also going to use the intermediate value theorem to prove the existence of a zero of a function. In this section, we use limits to define continuous functions, and then we examine their behavior. Now, intuitively, we regard a continuous function as a function whose graph has no breaks, holes, or vertical asymptotes. So in other words, it's continuous if I never have to pick up my pencil to graph the function. So we're going to define continuous functions using our knowledge of limits, but first what we're going to do is take a look at graphs of functions that are not continuous at some value c. So as you can see, I would have to lift my pencil as I draw the graph of each of the functions pictured below. Now I want to take a look at each one individually. Alright, so as you can see in our first figure here, f of c is not defined because at c we have a hole. Now we can also say that the limit of this function as x approaches c is not equivalent to f of c. So later on we're going to expand on this idea. Now in our second graph, this time f of c is defined, okay? But we can also say here that the limit as x approaches c of our function does not equal f of c. Now in our third graph, once again, f of c is defined here, but as we look at the limit as x approaches c from the left and as x approaches c from the right, our limits are not the same. So here, the limit fails to exist as x approaches c. And finally, in our fourth graph, we see here that when x is equal to c, our function is undefined. We have that vertical asymptote. So once again, we would say here that the limit does not exist, but we would specify, because we're reaching that vertical asymptote and we're heading towards positive infinity here, that the limit as x approaches c is infinity. Now, a function f is not one of the types of functions graphed here below if it can satisfy three different conditions. Our first condition is that our function must be defined at some value c. Okay? So in other words, f of c must exist. Now our second condition says that the limit of our function as x approaches that c value, that it must also exist. And then finally we have a third condition. We want to know, is the limit as x approaches c equal to our function when x equals c? Now, if we can say yes to all three of these conditions, then we say that our function will be continuous at c. Now, it is important to note here that if a function satisfies condition 3, that it must also satisfy condition 1 and condition 2, because obviously our function would be defined at x equals c, and the limit would also have to exist as x approaches c. So that idea actually leads us to a definition that we're going to use for when we decide if a function is continuous at some value c. Okay, so a function f is continuous at x equals c if and only if the limit as x approaches c of your function is equal to f at c. So whenever you're asked to prove or determine if a function is continuous at some value c, you're going to have to show specific steps in order to justify or prove that your function is continuous at a single point c. Or we say that it shows continuity at a point. So what I would like to do, just to practice this idea of showing and demonstrating that a function is continuous at some value c, I would like to use this graph of f of x to the right, and I want to determine at certain values of x if the function is continuous at those values. So we're going to use x equals 3 and x equals 2. So our first step here is to evaluate our function at x equals 3. So at x equals 3, we see that our function is equal to 2. So f of 3 is 2. We also want to evaluate our function as x approaches, evaluate the limit of f of x here as x approaches 3. So in this case, the limit as x approaches 3 of our function, we can see that the values from the left and from the right approach 2. Now, if we determine that the limit is equal to the function's value at x equals c, then we can say that this point is continuous, this graph is continuous at the point c. Now clearly in this case we do see that f of 3 is equal to the limit as x approaches 3. Okay, so in that case our function, we would say, is continuous at 3. So f of x is continuous at x equals 3. Now when we look for the continuity of our function at x equals 2, we want to evaluate our function when x is 2. So here we see that at x equals 2, f of x is equal to 2. So f of 2 is equal to 2. Now the limit as x approaches 2 from the left and from the right that limit here is 1. So our limit as x approaches 2 of our function, this is 1. Now clearly we can see that the limit is not the same as the function's value at x equals 2. So here in this case, f of x, so whoops, let's use f of 3. So f of 3 does not equal the limit of our function as x approaches 3. So in this case we would say that f of x is not continuous at x equals 2. So I know you can tell that from the graph, but if you're not given a graph and you're asked to determine if a function is continuous at some value c, you're going to have to make sure that you show each of these individual steps. Now, an important fact that we make use of quite often when determining if a function is continuous at some value of x is the fact that a polynomial function will be continuous at every real number c. And because a rational function, remember, is simply the quotient of two polynomial functions, we can say that rational functions will be continuous at every real as well, as long as it's in their domain. And the reason why we specifically write here that it has to be in their domain is that obviously if it's not in the domain of that rational function, then that means there's either a hole that occurs for that specific x value, or that x value creates a vertical asymptote, in which case clearly that rational function will not be continuous at that specific x value. And finally, I just want to note that trig functions, log functions, and exponential functions are continuous at every real number in their domain as well. Okay, now I'm actually going to skip to example 2, and I would like you guys to try example 1 on your own. If you want to show that f is continuous at a certain value, remember you have to follow 3 steps. So please work on that and check with the key just to make sure you understand that concept. And then we'll work on 2a, and then we'll actually come back to this definition up here before we move on to b. So in example 2, we're asked to find the values for which our function is continuous. So if we look at our function, we have a rational function. Now, if you remember from our fact above, a rational function will be continuous at every real except for the values that are not in the domain of that rational function. So in this case, we would want to factor first just to check if there are any holes in that function. Okay. In this case, there are no holes. So if we found a hole, that would be a value for which our function would not be continuous, so we would have to make sure we exclude that value. But in this case, there's no holes, so the only time this function will not be continuous is when your denominator is equal to 0, because that's where you'll have a vertical asymptote. So we are always going to make sure that we set our denominator equal to 0, because that's when your function values are obviously undefined. So we have x equals -1/2. So if we write, we want to show, remember, all of the values for which the function is continuous. So the only value we have to exclude is this -1/2. So we're going to do this with interval notation. So we say that our function is continuous on the interval from -∞ to -1/2. It's the open interval. And then from -1/2 to +∞. Okay, so these are all of the values for which your function will be continuous. Now, to find the values for which our function in part B is continuous, we actually want to make use of this theorem listed here. So let's let f of x be defined on a closed interval from a to b. Now we can say that this function is continuous on that closed interval a to b if it is continuous on the open interval from a to b, and if in addition we see that the limit as x approaches a from the right is equal to our function value when x is equal to a, and if the limit as x approaches b from the left is equal to our function value when b is equal to, or I'm sorry, when x is equal to b. So I think this theorem is actually easier to understand if you can see a picture. So I'm going to draw a quick little sketch here. So basically we're looking at a function that is defined on a closed interval from a to b. So we've got essentially a function with endpoints. One of the endpoints is at x equals a, the other endpoint is at x equals b. So we say that this function is continuous on the closed interval, and again it's closed because we're defined at x equals a and x equals b. There's closed circles here. So it's continuous on that closed interval if it's continuous on the open interval from a to b, and clearly here you can see there are no holes or breaks in that graph. Now the second part of that theorem states that you need to check the limit as x approaches a from the right. So we check that limit as x approaches a from the right, and that limit should equal the value when your function is evaluated at x equals a. So if f of a is equal to the limit as x approaches a from the right, and if the value over here, f of b, is equal to the limit as x approaches b from the left, then we say that that function, so let's show that right here, so f of b should equal the limit as x approaches b from the left. Then we say if those conditions are met that this function is continuous on the closed interval from a to b. Now I want you to notice that in the notation here of this theorem, they didn't use the limit as x approaches a from the left, because obviously you can't approach a from the left because the function doesn't exist to the left of a. And likewise, you can't approach b from the right because the function does not exist for those values. So when we look at a function here, like h of x, and we want to decide what values this function is continuous for, we have to consider, in this case, if there are endpoints. Alright, so the graph of h of x is actually a circle. It's the top half of a circle. The radius is 4, so here we have an intercept at 4, 0, and then negative 4, 0. So this is definitely a function with endpoints, and we want to know if it's continuous on the interval from negative 4 to 4, that closed interval. So what we would test is to see if the function is defined at x equals negative 4 and at x equals 4, and then we also want to know what the limit as x approaches negative 4 from the left is, and the limit when x approaches 4 from the right is. So we'd evaluate both of these things. Now in this case, if we evaluate f of negative 4, we have 0, and the limit, the limit as x approaches negative 4 from the right of this function here, let's just call it, oh, it's not even f, sorry, I'm using f and it's supposed to be h. Okay, so as h of x approaches negative 4 from the right, we see that that limit is also 0. Now if you check your other endpoint, you're going to want to evaluate h of 4 here, so we get 0. And then we want to know if the limit as x approaches that endpoint, the endpoint on the right, from the left. Okay, so the limit as x approaches 4 from the left, we want to check that, and we see that that value is also 0. So because the function on the left endpoint is the same as the limit when it approaches from the right, because obviously you can't approach that function from the left. Okay, but if you see that that value is the same, and on the other side, if you test and your function value on the right, so that right endpoint is equal to the limit as x approaches that value from the left, if those are equivalent, then you can say that this function is defined on that closed interval a to b, and it's continuous on that interval. So this is how, oops, I don't know why I just wrote a to b. We would write our answer here for the values for which this function is continuous as the closed interval from negative 4 to positive 4. Now let me erase this work real quick. So let's say you don't know what the graph of a function looks like, and here we have a square root function, right? Well, what we want to do is define basically where this function is, or the domain of your function actually. That's what you're typically finding when you want to find the values for which your function is continuous. You want to find the domain of your function. So in this case, if I wanted to find the domain of this square root function, what I have to do is set the inside greater than or equal to 0, okay? Because it's got to be positive on the inside. Now, when I solve this inequality, basically, I showed you a couple different ways back in the day 1 review of pre-calc. Remember, when you do this, you can graph it if you need to, but this would be the graph of a parabola that opens down, and it has intercepts at 4 and negative 4. So you're looking for the values of this function that give you positive values, so that's going to be from negative 4 to positive 4. So that actually is the domain of this function, which matches what that closed interval is as well for where the function is continuous. Now, this relied on knowing what the graph of that function 16 minus x squared looks like, but let's say you don't know what that function looks like. What you do is you pretend like you're solving that, and then you find your key numbers. The key numbers here would be 4 and negative 4, and then you have to test the interval. This is all going back to stuff from first semester, but you have to test that interval to see where you have you know, negative or positive values. So you just look at the factors. I should have factored this, sorry. So you have 4 minus x and 4 plus x. And then you test numbers inside the interval from negative infinity up to negative 4, and then from negative 4 to positive 4, and then from So that was this interval here. Sorry, I'm running out of room here. And then this interval would be 4 to infinity, and so on. And you just double check each of these intervals by plugging in an actual value here into that function to see when you get positive or negative. So obviously the only time when you're going to get a positive is between -4 and 4, and that includes when x is equal to -4 and when x is equal to 4, because you're testing to see when it's greater than or equal to 0. Okay, so sorry, I kind of went off on a tangent there, but basically you're finding the domain of a function to figure out where the function will be continuous. Okay, now I'd like to bring our attention back to those graphs that we discussed at the very beginning of our lesson. Remember, those were graphs of functions that were not continuous at a certain value c. So here from each of these graphs, you can clearly see that to graph these sketches here, I would have to pick up my pencil to continue to graph them. Now, when you have a discontinuity like this, we classify it with in three different ways. Okay, a removable discontinuity occurs when you literally remove a point from the graph. So even over here, this is called a removable discontinuity. Even if your function is defined as a different value, we call this a removable discontinuity if we've removed a point from the graph. Okay. Now, a jump discontinuity is called that because, as you can see here, the function values jump and continue on a different path. So basically, the idea here, not just that your value changes at x equals c, that you have a jump here, but that the limit approaches two different values from the left and from the right. Okay. And then finally, the third classification is an infinite discontinuity. Here, as you can see from the graph, you would have a vertical asymptote in the graph of that function, and they can go, to positive infinity both together, or they can go in different directions, or they can go into negative infinity. Each of those would be considered an infinite discontinuity, and it occurs specifically when you do have a vertical asymptote. Now, when you're given a graph, obviously it's really easy to see the type of discontinuity. The hard part is when you're just given a function and you're asked without a picture and without maybe even knowing how to graph it, you're asked to figure out what type of discontinuity occurs. So we're going to do some problems here just to get you used to the idea and recognizing what type of discontinuity it is at first, and then we'll see some specific examples. So real quickly, let's just get used to the terminology. We want to know what type of discontinuity occurs at each of the x values listed for this piecewise function graph to the right. So at x equals -2, okay, we're looking at a removable discontinuity. It's a removable discontinuity because I have a hole in the function, and even though that function is defined, it's called a removable discontinuity because we've removed the point -2, 1. Okay. Now at x equals -1, here we have a jump discontinuity, and it's not just because the fact that they're not defined here, it's because the limit as x approaches from the left and the limit as x approaches from the right, those limits are two different values. Okay, so this would be a jump discontinuity. Now at x equals 1, obviously since these are heading to positive infinity, here we have a infinite discontinuity. And specifically what you're looking at here is the fact that it's a vertical asymptote. Okay. And then finally at x equals 2, this is simply a removable discontinuity because we have a hole in our function right there. The point has been removed. Okay, so obviously those were really easy when you're looking at a graph, but here in problem 4 we're asked to determine where the function is not continuous and to specify the type of discontinuity that occurs when we're just given a function. So what we're going to do here is look at this function. Now it's a rational function, remember. It's going to be continuous at all values of x except for which are not in the domain of the function. So basically what you're looking for here are the values that make a hole in the graph or make a vertical asymptote. So when we factor the denominator here, we end up canceling out a common factor x minus 5. So there is a hole at x equals 5, which means that this is a discontinuity for that graph. Okay, and at that discontinuity, so at x equals 5, you'll have a removable discontinuity. That's the type of discontinuity because it's a hole. Now we also have, so we end up with the function 1 over x plus 3, right? After we factored and canceled. Now in the graph of this function here, we have a vertical asymptote at x equals 3, negative 3, sorry. So at x equals -3, there is a, I almost said horizontal asymptote, sorry. There is a vertical asymptote. Okay. Now in this case, it doesn't ask us to specify which direction, those values approach from the left and from the right. Are they going to positive infinity or are they tending towards negative infinity? We're not asking that. We're just asking for the type of discontinuity. So because we have a vertical asymptote, this type of discontinuity is classified as an infinite discontinuity. Okay? Okay, here in question 5, we're asked to determine the value of a that would make our function continuous. So here in example A, we have a piecewise function, and this piecewise function is defined as the sine of x over x for all values of x not equal to 0. Okay? Then, when x is 0, we have it defined as some constant a. Okay, so the first thing I want to do to tackle this problem is to think about where my piecewise function here may be discontinuous. I want to know which values of c would make our graph here discontinuous. So I'm going to analyze first the sine of x over x. Now this function here is continuous at every value of x except for when x is 0, because obviously you can see that the denominator here would be equal to 0, but the reason why our function is continuous everywhere except when x is equal to 0 is because you're looking at a sine function. Remember, the domain of a sine function is all reals, so that means the function is continuous for all reals, except obviously when you divide by 0. So if we think about what this piecewise function would look like if we were to graph it. Now I don't necessarily know what the sine of x over x exactly looks like, but I do know that it's continuous for every value of x, so maybe it comes in like this, but as soon as it gets to x equals 0, we have a hole. Okay, because at sine of 0 over 0, we have that indeterminate form 0 over 0, so that's indicating a hole in our function. So if we want to make this function continuous everywhere for every real, then we need to define at x equals 0 a value that's going to make us allow us to draw this in so that we never have to lift our pencil. So what we want to know here is what our function approaches from the left of 0 and from the right of 0. In other words, we want to know what the limit as x approaches 0 of the sine of x over x is. So I kind of forgot that when I designed this problem, we haven't actually gotten to this particular limit. This is a really popular question that the AP folks will ask you about, and this is something that we do get to in chapter 2, so we figure out a way to actually find the limit as x approaches 0 sine of x over x, but as of right now we don't have enough information or enough skills to be able to evaluate this limit, so I'm just going to tell you what it is. So the limit as x approaches 0 from the left and from the right of sine of x over x is equal to 1. So knowing that fact, what we need to do is ensure that when x is equal to 0, our function's value is going to be 1. So in other words, we want f of 0 to equal 1. So we want the function, let me start over. We want the limit of our function as x approaches 0, okay, to equal our function value at x equals 0. So remember, if this statement here is true, then your function would be continuous at x equals 0. And right now, that's the only place where our function has a discontinuity. So what we need to do is define f of 0 to equal 1, right? Well, that means then that a, this value here, should equal 1. Because at x equals 0, we define that function's value to be 1. All right, so that's our answer. This is the value for which our function would now be continuous for all reals. Now for question B here, we're asked to find the value again of a that will make this function continuous. So here we have a piecewise function. Now in this piecewise function we have a split at x equals 3. So when x is less than or equal to 3, our function is defined by ax plus 1, and when it's greater than 3, we're defining it as ax squared minus 1. So we want to make sure that we don't have a jump discontinuity at x equals 3. In other words, we have to make sure that our function will satisfy 3 conditions at x equals 3. Condition 1, h of 3 must exist. So in fact it does here. If you plug in x equals 3, this top line defines your function value at x equals 3. So we end up with h of 3 equaling 3a plus 1. So I'm literally just substituting 3 into the function for x. Now our second condition is that the limit as x approaches 3 has to exist. In other words, your left-hand limit must equal your right-hand limit in this function, since we do have a split at x equals 3. So we want to make sure that the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right. So that's what we're going to work on trying to ensure. If we can ensure that this is true and that these two values are equal, so the limit of our function at x equals as x approaches 3 is equal to h of 3, then we can say that there is continuity here at x equals 3. So if we want to make sure that the left-hand limit is the same as the right-hand limit as x approaches 3, what we're going to do is set these two limits equal to one another to solve for a. So when I approach 3 from the left, I'm using this function here up top. So to evaluate that limit, remember you just plug in the value, so you end up with 3a plus 1. That's the left-hand limit. Okay, so this is the value here, 3a plus 1. Now the right-hand limit will be given by this function here. So I evaluate that limit by plugging in 3 into the function, and I end up with 3 squared times a, so that's 9a minus 1. So really all I'm doing is solving this linear equation. Okay, so if I solve here, I get 6a is equal to 2, so a will equal 1/3. So that's the value that makes this function continuous. Okay, now we can actually verify that if a is 1/3, our function is continuous at x equals 3 by showing that this statement here is true. Okay, so let's find h of 3 first. H of 3 we know should be given by 1/3 times x plus 1. So we evaluate this function here when x is equal to 3, and we end up with 2, because 1/3 times 3 plus 1 gives me 2. So h of 3 is 2. Now we also need to check that the limit as x approaches 3 is also 2. Now we already know what the limit will be from the left-hand side because we just evaluated that function when x is 3. So let's check the bottom functions to see that the limit as x approaches from the right is also going to be 2. So if we plug in our function here, we have 1/3 x squared minus 1. We want to plug in 3 into that function. We have 1/3 times 9 minus 1, so 3 minus 1 is 2. So we know now that the limit as x approaches 3 of your function will equal 2. So because these values are the same, then your function is continuous at x equals 3. Okay, now I know you're probably thinking, why did we do all of this work here when everything just really boiled down to solving an equation where you took your function here and the other function and set them equal to each other when x was equal to 3. And that's really all we did algebraically, right? We solved this equation, we got our answer, a is 1/3. But really, calculus is about a method, and it's not just about computation. So the theorem here that we're relying on is proving that a function is continuous at a certain value. And to do that, you have to show 3 different conditions. Okay, now do I expect you to do this on your homework every time? No, I don't. You're just going to answer the question, and to answer that question, this is literally all the work that you would need to show. But I need to make sure that you understand why we can set up this equation the way we did, and it's because we're trying to prove that these 3 statements hold true. Now, as a consequence of continuity, we have this intermediate value theorem, which states that if you have a function f and it's continuous on the closed interval from a to b, and d is a number such that f of a is less than d, which is less than f of b, then there exists at least one number x such that x falls between a and b, such that f of x is equal to d. So let's take a graphical approach to understanding that theorem. So here we have some function that's defined on a closed interval from a to b. So here we have f of a, here's f of b. Now let's suppose that we have some value d, okay, that falls between f of a and f of b. Our theorem states that there must be some x value that falls between a and b such that f of x is equal to d. So simply put, if a function is continuous on a closed interval from a to b, then it takes on every value between f of a and f of b. So in our very first example here, it asks us to show that for this particular cubic function, there is an x that falls between 0 and 5 such that g of x will equal 27. So we're going to want to show the endpoints of this particular function between 0 and 5. So if we take g of 0, we end up with 0 minus 0 plus 0 minus 9. So g of 0 is equal to negative 9. Now g of 5 is going to be 5 cubed minus 5 times 5 squared. So actually those will completely cancel. And then plus 8 times 5 minus 9. So we end up with 31. So if we look at this as a closed interval and we think of it as just the endpoints, we have a left endpoint at 0, negative 9, and a right endpoint at 531. So it's just coming from, here. Okay, so we don't really know what's going on in between the function, like how we would graph it, and we don't really care about the function values outside of this interval from 0 to 5. But basically what our intermediate value theorem states is that if you have some y output here, 27, and it falls between the y outputs of whatever restricted interval you're looking at. In this case, we have an endpoint, a left endpoint at negative 9 and a right endpoint at 31. Clearly, negative 9 is less than 27, which is less than 31, right? So that means that we must be able to find an x value that falls between the 0 here and the 5. So it falls between a and b. Now, it's important to note that the intermediate value theorem only says that the function will take on the value of 27 somewhere between 0 and 5, somewhere between our a and b, but it doesn't say what the function value will actually be. It doesn't give you what the x value is. It only says that that value does exist. So our intermediate value theorem tells us that a function will take on some value of d somewhere between a and b, but it doesn't tell us where it will take that value, nor does it tell us how many times it will take that value. So that's an important idea that you're going to want to remember about the intermediate value theorem. Now I'm just going to erase really quick, and I want to actually formally write up how we can show that there is some x between 0 and 5 such that g of x is 27 for this particular polynomial. All right, so we have g of 0 was -9 and g of 5 was 31. All right, so what we've shown is that g of x, first of all, is continuous, right? So our function is continuous. That's important here too. Since g of x is continuous, and we can see clearly that g of 0 is less than 27 is less than g of 5, so in other words 27 falls between g of 0 and g of 5, then by our intermediate value theorem, okay, then by the intermediate value theorem, there must exist. It doesn't tell us where it exists, but there must exist some x, so it's in the interval from 0 to 5, okay, such that g of x will equal 27. Okay, now finally, as an important result of the intermediate value theorem, we see that if f of x, a function, is continuous on a closed interval from a to b, and if your endpoints f of a and f of b have opposite signs, then you'll have at least one solution to the equation f of x is equal to 0 in your open interval from a to b. So just going based off of this picture here, we have a closed interval from a to b. Our function is defined on this continuous closed interval. So what this is saying is that if you have f of a here, and if you notice, f of a is positive, okay? So f of a is greater than 0. And down here we have f of b, which is less than 0. Then we have at least one 0 between those endpoints right here. So we have at least one 0. And again, if you compare the endpoint, say we have another closed interval from b to c here, okay? So it's defined on this closed interval from b to c. You can see that if f of b is less than 0 and f of c is greater than 0, again you will have one solution to the equation f of x is equal to 0. In other words, you'll have 1, 0 of the function. So in our very last question of the lesson, we're asked to prove that this equation has at least one solution between 3 and 4. So by the intermediate value theorem, if we can show that our function will have opposite signs when x is equal to 3 and when x is equal to 4, then we can prove that there has to be at least one solution between 3 and 4. So if we evaluate, f of 3 is going to be -3 and f of 4 is +7. So we do have a sign change here, which is going to indicate that there is at least one solution between 3 and 4. Now again, it doesn't actually tell you where the solution is or what the solution is. It just says that it's somewhere between 3 and 4. So again, we would prove this by saying that since our function is continuous, okay, and we can also see that f of 3 is less than 0, which is less than f of 4, okay, then there exists an x, so this x is between 3 and 4, such that f of x is equal to 0. In other words, you've got a solution between 3 and 4. All right, so that's the end of the lesson. I know it was kind of a long one, but make sure you come into class ready to work and ask good questions. See you tomorrow.